Okay, we'll get back to 7.1 here. So the idea is we're learning integration by parts. Here's the formula. Okay, so we need to come up with a u part and a dv part. Okay, for the integrand if it involves integration by parts. So we looked at these first two examples here. Let's try this one next. We want to integrate the ln of x. Okay, so we know the derivative of ln of x, that's 1 over x, right? This is asking for the antiderivative of the ln of x. So I need to come up with a u part and a dv part. There's only one option for u, and that's to let u be the ln of x. See, I wouldn't let dv be the ln of x because then I need to know v, which is asking for the antiderivative of the ln of x. Well, that's what the problem is asking for in the first place. So let u be the ln of x, dv is the rest of this integrand, dx. The derivative of the ln of x is 1 over x dx. The antiderivative of 1 is x. And by the way, don't forget about your dx's, okay, your plus c's and stuff like that. That's very important stuff, okay? So we have now the integration, now the formula for integration by parts that we're going to use here. So u times v, that's going to be x ln x, okay, minus the integral for v du. Okay, v is x, du is 1 over x, those cancel, that's going to be 1, and then dx is going the integral there, okay. The antiderivative of 1 is x, so the antiderivative of the ln of x, that'd be x ln of x minus x, and then plus a constant. Okay. Now, usually integrals involving the ln function are going to be where u is going to be the ln function. Not always is that the case, but usually that's going to happen. Okay, so like in this problem here, we're integrating t squared ln pi times t dt. Okay, well, I'm going to let u be the ln of pi times t. I would not let dv be the ln of pi times t because this is the antiderivative of the ln of x, right? So the antiderivative of the ln of pi times t, that'd be, something with the u substitution in it, and have this, and u then would be t squared, du, therefore would be 2t, so you'd have to multiply, this guy by 2t. That's not making this integral easier than what it was, okay? And the idea with integration by parts is to make the integrand easier than what it was, okay? Something usually that you can get your hands on then right away. So I'm going to let u be the ln of pi times t, dv would be the rest of this integrand here, t squared dt. Du then would be the derivative of the ln of pi times t. That's going to be a chain rule. So it'd be 1 over pi times t times the derivative of pi times t, that's pi. So you got pi divided by pi times t, the pi's cancel, leaving you with 1 over t, and then dt. Again, don't forget about that. The antiderivative of t squared would be 1/3 t cubed. Okay, so now using the formula for integration by parts here, we got u times v, that's going to be 1/3 t cubed times the ln of pi times t, minus the integral for v du. Okay, so minus 1/3, that's a constant that can come out of the integral, times t cubed divided by t, that'd be t squared, and then dt is going to go in the integral. Okay, the antiderivative of t squared would be 1/3 t cubed. 1/3 times 1/3 is 1/9, and then t cubed. So my answer then will be 1/3 t cubed times the ln of pi times t minus 1/9 t cubed, and then plus a constant at the end. Okay. The next one here is where we're integrating theta cubed times cosine theta squared d theta. Okay, now sometimes you're going to have to, incorporate multiple techniques into integration. Okay, and in general, integration is way more difficult than derivatives. Okay, because the thing with derivatives is like I can give you guys any function and you can know the derivative. Okay, whether it be a product rule or a chain rule or something with the trig functions or ln function, whatever. Okay, like there's always a way to get the derivative. And that is not the case with antiderivatives. Antiderivatives are way more difficult because there's no set of hard fast rules to follow. Okay, and also we'll see this later, but not all functions have an antiderivative. Okay, like sometimes you could be doing an impossible problem. Okay, if I were to integrate just cosine of x squared, that's an impossible integral. Okay, there's no way to do that integral. Okay, again, we'll learn about that later. So if I use a u substitution on this, or a t substitution, so the first example that I showed you was where you're integrating x sine x dx, and we got that by integration by parts. Well, if I were to let t be theta squared, dt is 2 theta d theta, and divide both sides by 2, so 1/2 would be coming out of the new integral involving t. So you're going to have 1/2 times, okay, theta squared is what you're calling t. You got another theta, okay, which is theta d theta, that's the part that is dt. And then you got cosine of theta squared is t. Okay, so here's my new integral then. 1/2 the integral for t times cosine t dt. Now that looks very similar to what we just did over here in our first example. Okay, just instead of a sine x, I got a cosine t. Well, I'm going to use integration by parts. So u is t, dv is cosine t dt. Again, I would not have those switched because if u is cosine of t and dv is t dt, the antiderivative of t is 1/2 t squared, and that's not making the integral look any easier than what it was if I increase the power to 2. Okay, so I got to, I again look for those situations, and if you don't have the right parts set up, consider flipping the parts. That sometimes does the trick there. Okay, so if I let u be t and dv be cosine t dt, then u times v is 1/2 is in front of the integral, right? So I got 1/2 times t times sine t minus 1/2 times the integral for v du. V is sine t. So you're going to be integrating sine t and then stick a dt at the end. Okay. The antiderivative of sine t is negative cosine t. I've already got a negative in front of the integral. So the opposite of a negative is a positive. You're going to have 1/2 t times sine t plus 1/2 cosine t plus c. The last thing to do would be, my original integral was involving theta, so I'd want to give an answer involving theta. Well, t is theta squared. So where I see t here, I'm going to replace those t's with theta squared. Okay, so my answer would be 1/2 theta squared times sine of theta squared plus 1/2 cosine of theta squared plus a constant at the end. Okay. And one nice thing about integrals is that I can always know if I got the right answer. Okay, I can check. Okay, if I take a derivative of what I think is the answer, I should get right back to the integrand. Okay, that will happen. Why don't we try this next example here? Now, usually when you have problems involving integration by parts, usually u can only be one thing and dv can only be one thing. Okay, it's very rare to have it flip and still get the same answer. So like in this problem, you're integrating e to the x times sine x dx. Okay. If you let u be e to the x and dv be the rest of the integrand, sine x dx, then that's a way to start. Now in this problem, it does not matter what you let u and dv be. Like if I were to let u be sine x and dv be e to the x dx, I would still get the same answer. Okay, that would happen. That usually does not happen though for like nearly all these problems. Okay, usually there's only one way to do the problem. So we'll start with this setup here. Du would be e to the x dx, and v, the antiderivative of sine x, that's negative cosine x. Okay, so I got u times v, that's negative e to the x cosine x, and then minus the integral for v du. Okay, minus a negative means plus the integral for v du. So minus the integral for e to the x cosine x dx. Well, okay, let's consider using integration by parts again. Now on this integral, okay, sometimes you need to use integration by parts a couple of times. So if we do this again, let's let u be e to the x and dv be cosine x dx. Du is e to the x dx, and v, the antiderivative of cosine of x, is sine x. Okay, so I'm going to have negative e to the x cosine x plus u times v, that's e to the x sine x, minus the integral for v du. Okay, so minus the integral for e to the x sine x dx. Okay, now if I compare this to what I had originally, it looks like I just made a big circle. Okay, but the next thing I'm going to do is I'm going to use some algebra. Okay, use some creativity, and that's sometimes the case that goes on with integrals. So I have, I like this is my unknown. Like I want to find the value of this integral. Okay, so I can think of this as an equation, where I got an unknown over here, and the same unknown I'm subtracting over here. So if I add the integral for e to the x sine x dx, then I've got two of these integrals over here. So I'm going to have 2 times the integral for e to the x sine x dx equals the rest of this, negative e to the x cosine x plus e to the x sine x, and then plus a constant. Okay, I'm calling this C1 just because this is not my answer. But of course, the last thing to do would be to divide both sides by 2. That way we'll have the value of this integral. Okay, so the integral for e to the x sine x dx is going to be 1/2 times e to the x. I flipped these two guys here and factored out an e to the x. So I got 1/2 e to the x times sine x minus cosine x, and then plus a constant, whatever this constant is. So, or you could say C1 divided by 2 is the same thing. Okay. We don't care what the constant is though. So, okay, we'll go ahead and stop right here, and I've got 2 more examples left in this section.